Previous video, we have discussed about DC characteristics of an op-amp. In this video, we will discuss about AC characteristics of an op-amp. Okay. But in the previously discussed slides, so this is a circuit diagram of offset voltage, input offset voltage. I'm not, that time I was not told properly what is IOS here in this VIOS. So here in this VIOS equal to VI minus V2. So how I'm writing this from this diagram. So this is the difference between VI and V2 is IOS. Okay. The difference between these two terminal is called VIOS, offset voltage, input offset voltage. So from this only I am taking VIOS equal to VI minus V2. Okay, so this only I am writing here. Okay, so from that diagram, I'm taking VIOS is the difference between VI and V2. So that only I'm writing here. So these steps I missed in the last video in the DC characteristics of an op-amp in the third parameter, input offset voltage. So kindly make a note of it. Okay. So now we will discuss about AC characteristics of an op-amp. So AC characteristics means DC means it affects steady state DC response. For small sinusoidal application, AC characteristics is affects only the two cases. Frequency response first, it will affect frequency response and then slew rate. Okay, so under AC characteristics, we will be discussing about frequency response and slew rate. Okay, so first we will discuss about frequency response. So for the ideal op-amp, for an ideal op-amp, please consider like this. This is frequency. This is gain. This y-axis is gain dB in dB. Okay. So for an ideal op-amp, the frequency response like this. Okay. Let's assume this is a 90 dB. Okay. So for an ideal case, the frequency response of an op-amp will be like that. Steady state. Okay. Steadily it will go up to infinity gain. Okay. So bandwidth for an ideal infinity and gain, it will maintain the gain same dB. Okay. At 10 Hertz, 90 dB only. At 100 megahertz also, it will show 90 dB gain only. So in all bandwidth, in infinity amount of bandwidth, the ideal op-amp maintains the gain value same throughout the frequency range bandwidth. Okay, but This is for ideal case. This is for ideal case. But practical op-amp, what they do? In practical, for a practical op-amp, this is frequency and this is gain in dB. Some up to some frequency range, it will maintain it 90 dB, and afterwards it will rolls off. Okay, the gain will rolls off from 90 dB for a practical case. Why? Why it's like that? The gain will be rolled off at high frequency. Okay, at 10 Hz, it will maintain the same gain range, and 100 Hz, it will maintain the same range, but afterwards, at high frequencies range, the gain will degrade all or roll down because of capacitive component in the equivalent circuit. Okay, so inside our op-amp, there will be some internal components like transistors, okay, capacitors, okay. So inside capacitor is there, okay. Due to the capacitive component in the equivalent circuit, this degradation, this rolled off will be taken place, okay. So due to the physical characteristics of BJT or FET, this rolled off will be taken place. For an op-amp, okay, for an op-amp, with one break or corner frequency, all capacitor effects represented by single capacitor. Okay, consider this circuit. It is the internal high frequency model of an op-amp. Okay, so the dash line denotes our op-amp symbol inside our op-amp. Like this only we are having. Okay, resistor is having this resistor name is RI. I didn't put here. This is RI. Please make a note. RI. And this is the open loop gain. AOLVD. Okay, this is the open loop gain. This diamond shaped symbol. Okay. So like this is the internal high frequency model of an op-amp with one corner frequency. One corner frequency because all capacitance is considered as a one capacitance element C here. Okay. Mostly for ideal case, we are having only one capacitance. Okay. Okay. So from open loop voltage from figure can be derived as we have to derive for open loop voltage. Okay. Okay. So here, according to voltage division rule, according to voltage division rule, V naught equals, okay, V naught equal V naught from which they are flowing through capacitance. V naught will be flowing. Okay, so capacitance value we have to return and divide by total resistance value. Here R naught plus C is a total resistance value into source voltage. Source voltage here is AOL into VD. Okay, so please recollect voltage division rule. What is voltage division rule? V naught equal to, from where we have to find voltage, that component we have to put top side. So in this case, C, capacitance. Through capacitance, the V naught we will be going to take. So C we have to put top, then divide by total resistance. So here resistance components are R naught plus C into voltage, source voltage. Source voltage here is AOL into V. Okay, that only I'm going to write here. Okay, so according to voltage division rule, first we have to write C. Okay, because from C only we are going to find V naught. Okay, C we have to write. We have to, can we write simply V? C? No. This is the reactance component. So we have to write C as 1 by J omega C. Like that we have to write that instead of C. Then total resistance R naught plus C. C we have to write, we should not write C as such. We have to write like this 1 by J omega C. Then into source voltage. Here source voltage is AOL into VD. Okay. So I'm drawing like this line. Okay. Then we have to simplify. How? 1 by J omega C. So can I take new slide? Eight. Yes. Okay. I am writing here V naught equal to 1 by J omega C divided by R naught plus 1 by J omega C into AOL VD. Okay. Then V naught equal to 1 by J omega C divided by 1 plus J omega R naught C whole divided by J omega C. I'm taking LCM AOL into VD here we are coming and equal to A. Okay, wow. A means gain. Gain means output voltage to input voltage V naught divided by this VD will come downwards. So VD equal to here J omega C will get cancelled. Then AOL divided by 1 plus J omega R naught C will come. Then AOL divided by 1 plus J. Instead of omega, I'm going to write 2 pi here. R naught C. Okay. AOL will come as such and 1 plus J F by F1. I'm writing like this. While where F1 equal to 1 by 2 pi R naught C. Okay, okay. So if we put 1 by 2 by R naught C as 1, sorry, F1. So we are changing the equation F by F1. Okay. So what is this frequency F1? F1 means what? F1 means corner frequency. Corner frequency or upper 3 dB frequency of an offer. Okay, this is called corner frequency. So in this frequency only the roll off will be taken place. Okay, from at a particular corner frequency only the roll off, the gain will get rolled off. Okay, so here we will be for A, gain A, we have to find magnitude as well as phase. Okay, We have to find magnitude and phase. First, we have to find magnitude. So, in this equation, I am taking absolute value, then AOL divided by 1 plus F by F1, the whole square, and root of, the whole root of. Okay. We have to square and take root for the absolute. So I'm taking like that only. This is called magnitude. Okay. Then phase we have to found. For phase angle phi equal to minus tan inverse F by F1 is your phase angle. Okay. So like this only we are finding magnitude and phase angle. Okay. So in this I was told one step. Do you remember? Corner frequency. F1 is your corner frequency. After corner frequency, the gain will get rolled down. So we will be seeing like this. This is the magnitude and phase. Okay, so here is our frequency response of an op-amp. Okay, here only I'm telling this is gain. Okay, y-axis denoted as gain and x-axis is your frequency range. At a particular corner frequency F1, the gain will get rolled up. Before that, the gain will maintain the same gain rate. But after the corner frequency, it will get rolled up into the 3 dB line and then degrade. Okay. So what it is mean? Means here we are having 3 stages. In the figure we are having 3 stages. This is F. Okay. So F less than F1 means what? And F equal to F1 means what? Then F greater than F1 means what will happen? So like these 3 cases we are having. So first case, F less than F1 means magnitude of gain is 20 dB AOL. This is first case. Then second case, F at equal to F1. Corner frequency means the 3 dB down from AOL in 3 dB will be taken here. Then after that, F greater than F1 means gain rolled down at minus 20 dB decayed. So this is the 3 cases of frequency response. Okay. This is for magnitude, open loop magnitude characteristics. Then we are going to see the phase characteristics. Phase characteristics, here we are marking y-axis as phase and x-axis as frequency. Here F1 will be our cutoff frequency, corner frequency. So here also at f equal to 0, phase angle 0 degree, no phase shift will be occurred. And f equal to F1 case, phase angle will be minus 45 degree. Then F greater than means F infinity, in infinity, phase angle will be minus 90 degree with single capacitance. Okay, so both the characteristics, magnitude, if you say magnitude and phase, both will be for single capacitance values only. We are taking single capacitance. Okay, because for ideal case we are having single capacitance only. For practical case, there may be more than one capacitive values. Okay, so here only one capacitance value, so we are having one corner frequency. Suppose in practical case we are having 3 capacitive elements, we are having 3 what three corner frequencies, F1, F2, F3. That is for practical case. We will see, we will discuss that also. Here you see this is a practical case of an op-amp. Here we are having three corner frequencies. Okay. I missed the marking here. Please note this is corner frequency 1, 2, and 3. Here we are having three corner frequencies. So at a particular corner frequencies, the gain will get degraded. Gain will get degraded. Gain will get rolled down. Okay. Okay. So the gain formula, we will take like this. A equal to AOL divided by, this is for multiple corner frequency in the practical cases, 1 plus J F by F1 plus 1 plus J F by F2, 1 plus J F by F3. Okay. So this is for what? Multiple corner frequencies case. Okay. So this is about frequency response of AC characteristics. Okay. For ideal case, gain will maintain the same throughout the frequency for infinity frequencies. But for a capacity, for a practical case, not like that. The gain will roll down at a particular corner frequency. So the roll down will be taken place because of the presence of capacitance elements. Okay, for an ideal case, there will be only single capacitance element. For a single capacitance element, we can discuss the magnitude response and as well as phase response. And for a practical case, there may be more than one capacitive elements. For that, suppose three capacitance means three corner frequency. So for that, we are having the frequency response like that. Second major parameter of AC character is slew rate. Okay, slew rate. What is mean by slew rate? This is about rise time of amplifier. Rise time of amplifier. The time the output takes to change from 10 to 90% of the final value for a step input. Okay, so that is called slew rate. This is about rise time. To take output voltage. Okay. For ideal case, response time is 0. For ideal case. Sorry, 0, not infinity, 0. Response time 0. Bandwidth will be infinity. Instantaneously, it will respond. Output voltage respond instantaneously for a change in input. This is for ideal case. But for a practical case, rise time will be different. Okay. For a large signal, VM will be greater than 1 volt. For a small signal, VM less than 1 volt. Okay, so like that, the response time will get vary. And also the output speed, the op-amp speed is limited by slew rate. Okay. You see, for wider bandwidth of op-amp, we are having better slew rate. Okay, slew rate is R. I'm writing SR. Okay. Altogether we put what is mean by slew rate? It is a maximum rate of change of output voltage caused by a step input voltage. Okay, it is a maximum rate of change of output voltage caused by a step input voltage. We can, the unit is volt per microsecond. Okay, for ideal case, SR infinitive maximum. For practical case, SR will be of 0.1 volt per microsecond to 1000 volts per microsecond. Okay. If this is ideal, this is practical. Okay. So for a better performance, SR should be higher. Okay. For a better performance, SR should be higher. What causes slew rate? Capacitor within or outside of them to prevent oxidation. We are having capacitor slew rate. This capacitance prevents output voltage from responding immediately to a fast changing input. This only we are having. Then the rate at which the voltage across the capacitor VC we can represent as like this. dVc by dG equal to I by C. We can formally note it as slew rate equal to I maximum by C. Okay, so this is the formula for slew rate. So slew rate is the what is that? The maximum rate of change of output voltage. Okay, so that is called slew rate. For ideal case, SR will be maximum, and for practical case, there will be 0.1 to 1000 volt per microsecond. Okay, so in this video, we discussed about two parameters of AC, that is called frequency response and slew rate. And in the upcoming video, we will be discuss about open loop and closed loop configuration. Thank you.